Welcome to the podcast Inside Brains. My name is Matthias Wittfurt. I'm a neuroscientist, psychotherapist, and performance coach living in Hanover, Germany. My task in this podcast is to interview top experts from brain research, psychotherapy, and coaching to dig up their best strategies and techniques, and to help make your life better by sharing information you won't get anywhere else. First of all, thanks to everyone who listened to the first English episode, in which I have talked to Guillaume Nery, a world-class freediver, about his techniques and experiences. The present episode is a very special one. Functional magnetic resonance imaging has been around for 25 years. Last year, in 2016, a scientific article has been published stating that perhaps 40,000 published neuroimaging works are flawed. This article, published in the prestigious journal PNAS, has brought the authors and its topic abruptly into the focus. Most media coverage drastically truncated their core message, stating only that fMRI produced incorrect results and that one analysis software contained a bug. Scientific colleagues vehemently criticized the far-reaching statements of the three authors. But what is actually true? Do we have to deal here with a bankruptcy of a whole scientific branch? In this episode, I'm going to talk not only to one expert, but to four new scientists about the subject. The first of them, John Dylan Haynes, is a professor at the Bernstein Center for Computational Neuroscience in Berlin, Germany, and director of the Berlin Center for Advanced Neuroimaging. He has become particularly known through his work on free will. For this work, he employed new methods which identify and classify recurring patterns in brain activation, which allow for conclusions about the underlying subjective processes by means of the fMRI data only. Hina Google is a professor for cognitive neurosciences at the University of Maastricht in Holland and developer of the commercial software Brain Voyager. His field of research covers the areas of high-field MRI and neurofeedback. As a third guest, I am very pleased to be able to interview one of the authors of this notorious study. Tom Nichols is a professor in Coventry at the University of Warwick in the Department of Statistics, as well as Senior Research Fellow at the Alan Turing Institute. He has published numerous papers, especially on statistical procedures in neuroimaging. The fourth neuroscientist is Hina Wittfurt, and apart from being my wife, she's head of the functional imaging group at the Hanover Medical School here in Germany. Her expertise is for sure how the brain regulates emotions. Together with me, she offers workshops for the analysis of neuroimaging data with the widely used software SPM. Before we jump right in, I would like to give those of you who haven't read or heard of this before an idea of what this infamous article is all about. First off, let me tell you that this is quite complex, far more complex than what was covered in the media. The gist is that the authors, Anders Eklund and Hans Knutsson from Sweden and Tom Nichols from England, wanted to check how some of the most widely used software packages for analyzing fMRI data behave regarding the so-called false positive rate. In statistics, this term refers to the probability of falsely rejecting the null hypothesis for a particular test. The null hypothesis is a general statement or default position that there is no relationship between two measured phenomena or no association among groups. For example, when testing a certain treatment versus a placebo, your null hypothesis would be there is no difference between the outcome of the treatment group versus the placebo group, i.e., their outcomes are the same. Now, the false positive rate is calculated as the ratio between the number of negative events wrongly categorized as positive and the total number of actual negative events. In other words, if you have false positive results, it means you have detected differences between your experimental conditions that are not actually there. In the article with the title Cluster Failure, Why fMRI Inferences for Special Extent Have Inflated False Positive Rates, nearly 3 million random task group analyses were performed to compute empirical error rates on real resting state data. Resting state data are obtained by measuring brain activity while the participants actually have no task in the scanner except from daydreaming. So you would expect that by randomly choosing two groups of subjects, the null hypothesis of no group differences in brain activation should be true. 3 of the most commonly used software packages were investigated: SPM, FSL, and AFNI. In AFNI, the authors found a 15-year-old software bug that was fixed by the developers along the preparation of the manuscript. Their main finding, however, was that under very unfavorable conditions, the empirically observed number of false positives was way higher than what was theoretically expected. The authors found that all 3 software packages performed poorly, in particular for very lenient statistical thresholds, such as, for example, p equals 0.01. This, of course, raised one major question: how many studies are affected? The authors scaled their initial claim of a massive 40,000 studies, which refers to an estimate of the overall number of fMRI studies ever been published, down to 3,500 studies, which might not have used appropriate statistical methods. Okay, so let's just dive into this topic. First, I asked Dina what her thoughts were when she read about the paper and saw headlines like the one in the Forbes magazine that tens of thousands of fMRI brain studies may be flawed.
I think it was a mixture of feeling defensive of my own work, because of course you kind of get protective. You don't, as a neuroscientist or neuroimager, you don't want to be told that everything you did is basically trash. So that was one part. But the other part was this nagging unease that maybe this is correct. And I think it was kind of like a mirror for every neuroimager's worst fears, especially for those who are not involved in developing methods and who are not as well educated in statistics, because at some point, you have to trust that the experts know what they're doing. And it was a mixture of defensiveness and unease and the feeling that it's necessary to revisit what we did and what we're doing and whether this is all correct.
Everyone seems to be very cautious because no one understands really every aspect of it.
Yeah. Yes, of course. I mean, that's very, it's very humbling if you think about the complexity of the data, the complexity of the analyses, and the fact that you don't understand every aspect of it, and yet you're publishing research using these methods Of course, that leaves a lot of room for doubt. And then being confronted by the media with, as I said, kind of your worst fear that everything you're doing is wrong, it's not a great feeling. But I think now it really depends on what you do with it. You can either stick your head in the sand and wait till the storm passes, or just throw everything away and say, well, now I'm gonna quit neuroscience and become a sheep farmer in New Zealand. Or you can try and do whatever is in your power to get over these problems. And I think that's hopefully what will come from this, is the drive to really make everything as waterproof as it can be in neuroimaging.
What do you think the opinion after these publications in the mass media would be for the laypersons? For people who are not in the field, to read this, who work in various areas. Do you think the trust in these results is somehow shaken, or what do you think?
I think it is, and I think that's a good thing, because I think also part of it is that the memory span doesn't tend to be quite long for these things. And also before this paper came out and before all this kerfuffle began, I think neuroimaging was on this pedestal. It was like the holy grail of science. Everybody was trying to prove their method, their points, their views with these images with brains and colorful blobs on them, even not knowing anything about neuroscience. Like, everybody was drawing on these findings to make their own opinion look more valid. And now a certain amount of cautiousness and being critical is not such a bad thing, I think, because in the end, it's a physiological measure. And what you see, these colorful blobs is a visual display of statistical values and nothing more. It doesn't say that this is true. It doesn't say that this is more important or more valid than any other physiological measure. And I think if that message gets out there, it's probably not such a bad thing. It was neuroimaging as a whole field was kind of, in my opinion, a little overvalued. It was, and I think part of it is because it has powerful images. It uses pictures of the brain and everybody can relate to them. That's more interesting than looking at a bar chart or a line graph that you get when you analyze other physiological measures.
So now to John Dylan Haynes, who is a professor at the Bernstein Center for Computational Neuroscience in Berlin, Germany. And while discussing with him the Eklund and colleagues article, I asked him what he has to say in favor of this work.
The paper by Eklund is very interesting because it tries to assess possible mistakes in statistical procedures in neuroimaging. And neuroimaging is a new field. It's only 25 years old, functional neuroimaging. And we continuously have to update and improve our procedures. And this paper is an important contribution.
Mm-hmm. Okay, so this is a general positive side. There have been quite a negative hype, I would say, about the results of the paper and the reflection of the conclusions in the general mass media. And What would you say what your concerns are regarding this?
The paper is an attempt to solve a problem that is unsolvable, which is to know exactly how strong mistakes we make when we make certain statistical assumptions. And as a scientific paper, it's a valuable contribution. It's not a final answer to this problem of statistics. It's one piece in a bigger puzzle of trying to improve statistical procedures in neuroimaging. The problem with the paper is that it makes exaggerated claims in its significance statement. So basically, the original version of the paper claims that the results question the validity of some 40,000 fMRI studies. Now, that's vastly overstated, and it's quite clear why, and that is that the big errors that they report, that they find, only occur under very specific conditions, and that is, technically speaking, when one uses a very liberal threshold for the statistical analysis. And most people using the statistical procedures outlined here use very conservative, not very liberal thresholds. And there the problems don't really occur. They occur a little bit, but they're not quite so dramatic. So this supposed impact that this would have in validating a major part of functional neuroimaging, it's simply not true. And this has gone completely out of proportion in the media. I'd like to give a different example. When Einstein published his theory of relativity, he didn't publish a significant statement that said all of old physics is wrong. Instead, it's an improvement that is really important, but it doesn't necessarily invalidate everything that has happened before, because statistical procedures are approximate anyway. There is no perfect statistical procedure, and all we can do is to publish more and more and more papers where we try and continuously improve these statistical procedures, and that's something this paper is doing. But just if we have a little improvement, it doesn't mean that everything that's happened before is wrong.
Okay. One point is that the study uses a large pool of real human resting state data. And there have also been raised concerns that maybe resting state data have also correlations in it. So there shouldn't be the assumption of a null hypothesis shouldn't be right there. How do you see this point?
If you want to validate a statistical technique, it's very important that you need to define what your null assumption is, your basic assumption is. So the way statistics works is that you say, I will assume that there's no effect on the data unless there's something very unusual that I can see. And this background of the data, the kind of normal behavior of the data, if there's no effect in there, you need to define what this normality is, what is a normal case. And the normal case that is used in this paper is actually not quite so normal because it's what's called resting state data. Resting state data are neuroimaging data that are acquired while people are lying in a scanner with no specific task. In these cases, people might be thinking about what they had for breakfast, or they might be anticipating what they're going to go to do this evening. But whatever they're thinking about, it's not constrained by the experimenter. And in these cases, we know that there's a characteristic network that becomes active in the brain. And the brain activity is not in some default or null mode, but instead it's very highly correlated. And this is very untypical for brain activity during tasks. And most statistics are applied to brain activity during tasks. So I'm not sure if the assumptions in this paper are statistically valid.
What are your implications of the work? What do we learn from this for future studies? Is it a very important point to share data more in the future?
One thing we can learn from this data set is that it points us in a direction which analyses to avoid. First of all, we have to avoid statistical tests of this type where we use very liberal thresholds. People haven't been doing that very much anyway, but it's good that it's spelled out now that we have to avoid these tests completely. Also, it points towards the certain software packages being more or less susceptible to these effects. I think that's very important as well. So in general, of course, the bigger picture question is, what can we do in neuroimaging in general to improve our techniques? What are the mistakes, the inaccuracies that we make with our research technology? And as in every field in biomedicine, where you have huge data sets and you have to rely on very rigorous statistical techniques, neuroimaging has to be very careful to avoid any kind of biases or tendencies or self-fulfilling prophecies in the data analysis. And this study points in this direction more. And there are several other measures that people can take in order to improve the accuracy of neuroimaging data analysis. For example, one big initiative that is spreading through the field at the moment is to improve replication. The way to do this is that people will be more and more expected to upload the data that they acquire, including all the details of their experiment, to a web server so that other people can check their analyses. And also that other people can try out different analyses on the same data sets. So this spirit of open data is very important.
That this request of yours to share data and to make it replicable hasn't been in the past. Could it be that this reflects that some researchers aren't sure regarding their results, that they hold back because they know their statistic may be weak?
I think every field has its good and bad sides. So I think if you look in neuroimaging, it's first of all, one major reason why people don't in the past or didn't upload data onto these databases is that it's a pain to do so. So it's just a lot of work for no obvious benefit for the researcher in the short term. In the medium and long term, the whole of science and also the researcher themselves, I think, benefits from uploading the data. But I have to fight with students if I want to upload data. So they don't immediately see the advantage of doing so. And this culture is slowly spreading out in neuroimaging. I think it's very important to do so.
What are your personal advices for neuroscientists regarding, on the basis of this Eklund et al. Work? For first, of course, share the data, upload the data so everyone can take a look at this, take a look at these data and try to reanalyze the data. And second, I've heard that some people gave the advice to that it would be very important to inspect the time courses of your own data, that many people don't do this anymore for different reasons. How do you see this point?
There are many different things that need to be done in order to improve the quality of data analysis in neuroimaging. Certainly, it's not good if people don't have a look at the quality of their data before they perform data analyses. And there are more or less rigorous scripted ways in which people can check their data if they fulfill the quality requirements. These checks should always be done routinely and with standard settings, because otherwise This is one of the big problems with these complicated analyses. Otherwise, you can post hoc afterwards, if you don't like the result, change the selection of subjects, of data sets, etc. And I think these, what's called degrees of freedom in your data analysis, are one of the biggest problems if you're dealing with these complicated data sets. In fact, our lab, with a postdoc, Carsten Allefeld, and a PhD student, Joram Soch, we've been developing approaches that try and take the freedom for selecting parameters out of the hand of the researchers again, in order to avoid people playing around with these parameters and what's called p-hacking, trying to find the best analyses for their data that might give them a result that is more favorable. I have to say, these practices are commonplace all over science. It's not just a problem of neuroimaging, it's a problem in biomedicine, it's a problem also in computer science and pattern recognition to some degree. So it's not just a problem here. One of the solutions that is always discussed is pre-registration of the analyses, where the idea is that if you want to acquire data and you want to publish a paper, you need to specify before you've seen the data for the first time which data analysis steps and which statistical techniques you're going to be using. That way you avoid this problem of too many degrees of freedom in the data analysis, where people might hack the data and try and find a favorable result.
Mm-hmm. Yeah, I think it's of equal importance to teach good scientific practice, right? In general. So
I think the problem. I think one of the big problems with these complicated data analyses, it's not just a problem of neuroimaging. Any field has these complicated data analyses, genetics, for example, as well, or other fields of neuroimaging, is that there's a gray area between discovery and overfitting. So basically what this means is you acquire a data set, you have an a priori hypothesis about the effects that you expect in the data set, and you don't find them. Then you think, oh, well, perhaps it is because my data analysis wasn't suitable. You change the data analysis and you find, now it works. And the mistake was, for example, that I misestimated the time profile, the temporal profile of the result. Yeah, that will be a discovery. And in that case, what you need to do is you need to collect some more data in theory. And then validate, test whether this is really true or whether this is just some statistical chance effect that you observed in your data. So this is really important. That's the discovery side. The overfitting side is that you might just discover something that's just noise, and you think it's real, but in fact it's just some random aspect of your data. Like looking in the clouds and seeing faces and other things. That's overfitting. You're seeing structure where there is no structure. And an important part of science, an interesting part of science, happens exactly in this gray zone between discovery, the flexibility, the creativity of analyzing the data, and on the other hand of overfitting and overinterpreting the data.
So now let's move on to Hina Google, who is a professor of cognitive neurosciences at the University of Maastricht in Holland, and also the developer of the commercial software Brain Voyager, which wasn't investigated in this notorious work by Eklund et al. And I asked him what his overall impression of this work was.
I think that the paper might have had a good intention, but probably fall in the trap to be attractive for high-impact journals like PNAS, to sell it as an alarming paper. And so it might have did really some damage to the reputation of the fMRI field. But it is also a good paper. I would not say it's just a bad paper. It has also discovered some important insights in the structure of errors in fMRI data and resting state fMRI data. So I see also real value of the paper, but unfortunately the negative hype statements that 40,000 papers are now probably wrong, which the press kind of took up, they are really alarming. And I was just at the conference in Florence at Human Brain Project, and I hear that students or speakers who are not maybe statisticians say things like that. I have here some fMRI data, but as we all know, I'm myself not sure whether it's correct because we cannot trust fMRI. And that is a damage I just experienced a few days ago. And this is really alarming.
Yeah. One of the authors of this paper, Tom Nichols, based his entire career of the comparison of parametric and non-parametric inference methods. So he's one of the guys who's really into this kind of comparison. Do you think it's just far-fetched, the 40,000 number, or is there a completely false statement in the side of the work also?
I mean, I'm definitely sure that's a false, totally inappropriate statement, and I can explain why. But first to Tom Nichols, I mean, he has apologized. He wrote an erratum, so that these alarming sentences are no longer in the paper. So he estimates now about 3,000, which might be still very high, but nonetheless it's not 40,000. And he also made a very important small change in his erratum, which I found extremely important. Namely, he says that is problematic for weakly significant papers. That's what he writes now. So that means if you say up to a certain inflated false positive rate, that doesn't mean that the paper necessarily has reached that, right? And if people publish fMRI work, which kind of gets you normal p-values, and they're not maybe just 0.05 or 0.499 or very, very borderline. And many papers have, of course, that they're not depending on exactly this threshold. I would guess that only a small proportion of very, very weakly fishy papers, which work a lot to get something which is almost not significant. This amount of papers where this is extremely close to thresholding and where people probably have tried several things, they might fall under these 3,000, but not 40,000. And again, even there, it's not a proof that they are wrong. It's only clear that they made their threshold at the borderline, which is also, again, a convention we have. Even if it's 5% or even inflated to 20%, it still would mean that if they would replicate their study, they would 5 in 5 or say inflated 20 times by chance get this from 100. So it's again not a proof that their specific study is flawed. So we have to be very careful to interpret statistics here.
Mm-hmm. Isn't it the case that they put their fingers into a wound that many neuroscientists already knew? So one of the proposals of these authors were that data sharing must also come. Everyone has to revisit the data from other people. Isn't it true that you do underline this proposal? No, I would a little bit restrict it to evaluating. I mean, first of all, data sharing is a good thing. We should do it more. We should exploit and learn from other data. So I'm not against that at all. But I'm against that other people have now to check other people's data. They can, of course, but usually they want the data to do own analyses and maybe find something new in the data. But I think the good thing of the paper is that they let the people use available data to test how statistical routines operate under more realistic scenarios than if you simulate your data, right? In the past, people tested, including myself, people tested their methods either on small data sets, which might be flawed because they are selected in a certain way, or by generating simulated data which has certain properties of the errors in the data, of the noise in the data, but is not necessarily approaching the noise structure, the spatiotemporal properties of the noise in real data. So having these huge amounts of empirical data available for testing methods is indeed a good thing, because you might discover
that the modeling assumptions of some tools concerning the structure of, for example, the noise in this case in the data might be too short-sighted in the past and might have been to be extended in the future. That's actually the positive aspect of the paper, in my opinion, that they found that probably the modeling of noise is too simplistic of certain fMRI tools.
Mm-hmm. Your own development, Brain Voyager, hasn't been tested in this paper. Do you know why?
I don't know why. As far as I remember, I was not contacted by the authors, so I don't know why. I cannot tell you. I only know that in previous work, Brain Voyager was sometimes at least included, especially Tom Nichols cites a paper by Wu et al. That analyzed false positive rates, potential false positive rates, by using the so-called cluster threshold procedure, either by Gaussian random field or by simulation, Monte Carlo simulations. And in that study, Brain Voyager was included. It's a precursor of this paper. And they found that the Brain Voyager users behaved pretty okayish, much better than, for example, in FSL, where people used thresholds which are more in danger to suffer from these false positive problem. So in that sense, it was unfortunately not in this paper, Brain Voyager, but at least it was in previous work, which at least indicates that Brain Voyager does not suffer more than other softwares. If at all, it looks pretty good, like some others also, which look good. So there's a range, about 5-6 software packages they analyzed. And Brain Voyager they are definitely not on the low side. So that's reassuring that Brain Voyager is not kind of bad in that respect. But of course, also Brain Voyager, like other software, might have a problem here, which was not clear to me and users before, and that is related to this noise structure I mentioned before. So if the conclusion of the Eklund paper are correct, that the spatio-temporal structure of the noise is not modeled by the models we use at the moment, then of course also the models in Brain Voyager are not optimal. That doesn't mean they make big mistakes, but it could be that they also suffer to some extent from inflated false positives. And that's also why preventive steps have been taken in Brain Voyager already. So we kind of use for cluster size thresholding more conservative initial advice to users. So if they use a too lean threshold, too low threshold, we warn them and say, you might run in that risk of false positives, and please adjust it. So we then use as recommendation the threshold which turned out to be not vulnerable to this problem in any substantial way. So therefore, we did already some precursors. The second, if I may mention that, we also will implement permutation testing in Brain Voyager more now. We use it a lot already for machine learning tools, but not so much for statistics in Brain Voyager. But this also changed. It's now on the agenda at the top level to have soon a permutation testing. And Brain Voyager is a fast software, so I think for the normal 10, 20, 30, 40 subject studies, I think we will have it fast enough that people have not to wait too long. And therefore, it will be an option besides false discovery rate, Bonferroni, which is of course very conservative, and cluster thresholding. We will also offer permutation testing for single voxel and cluster analysis in Brain Voyager. These are conclusions from the paper, just in case people want to be even more protected with our software, then we will offer that to them.
Okay. I would like to ask a very specific question regarding the false discovery rate. So that has been included in the SPM package a couple of years ago, and it was kind of voted off the island. You have this option still in Brain Voyager, and it seems to be a very important and dominant way of analysis. Why is that so?
Yeah, this is actually this is funny because Tom Nichols, together with a co-author, I forgot now, was also introducing that method into the fMRI community. So the original false discovery rate was developed by two Israeli statisticians, Benjamini and Hochberg, but it was introduced to the fMRI community by a paper from Tom Nichols and a colleague. And that's interesting because now the recent paper and also a lot of the work in SPM and so on, still focuses more on the so-called family-wise error, right? So the difference is that with the family-wise error, you want to be sure that not a single voxel or a single cluster is falsely declared activated, right? So that's what you try to do. So over the whole brain, you don't want that even one pops up in a false positive way. And that is, of course, a fantastic goal, because you never make, so to say, a mistake if your p-values are really correctly reflected by your statistic. So the nominal p-value is really the one the statistics test, and that is the problem of the Acton paper. It's not always exactly like that. But given for the moment that the p-value you put in your software is really what you get protected for, then the family-wise error is somehow a good goal. But it makes has a big problem, namely that your beta error is big if you make the family-wise error for the alpha error. What that means is that you might overlook real effects in your data. And that's a severe problem. It is actually clear that there is, if you go fully for the family-wise error alone, you might make the other error big, that you overlook important information and make also wrong conclusions. And that's why I like the FDR, the false discovery rate, so much, because it has a slightly different statistical model behind, namely that we should correct with respect to the amount of activity in my data. What that means is, if I have a lot of very, very good voxels, because I can rank my p-values and look at this ranking, and I find I have a lot of good voxels, I can make my threshold relative to the amount of these voxels. And that means I tolerate, relative to the amount of declared active voxels, 5% as error. So that gives you another model on your data, namely you allow to see more and still have from that what you see, know that about 5% is on average false positive. This is a different model. And only if you really have data that kind of good p-values, only then you get these linear thresholds, which are kind of in between the alpha and the beta error. And if you have basically really just one voxel, which is somewhere activated, then the false discovery rate falls back to the Bonferroni method, which is the family-wise error method, the most conservative one. And so therefore it is a pretty good method, which if you really have weak data, spatially not much activity, for example, then you have also a hard time to get the significant with FDR. But if you have several regions or larger clusters which are active, the FDR already adjusts for that. And that's why I like it so much. But it's not the classical family-wise error model. It's another statistical approach.
Yeah. So you're not familiar with the reasons why this isn't included in SPM anymore?
Actually not. I don't know. I mean, it's clear that I think this has two answers. Maybe they like more family-wise error approach in SPM, but the second might also be that in their probabilistic thresholding approach, the Bayesian approach, I think they have a method which basically does something very similar like FDR. But honestly, I'm not sure why it's not explicitly included. Do you know?
No, I don't know. There seems to be a kind of method that you described that seems to be similar to FDR, but it's completely not transparent what SPM really does there. So yeah. It's just a kind of values you see on the table, but you don't know what really was going on. Mm-hmm. If we try to look to make an outlook in the future, there has been, maybe as a result of these negative hype in the mass media, the headlines in the heads of people that say neuroimaging results are wrong, completely wrong overall. So how do we cope with this in the future?
Yeah, that's the damage I mentioned earlier, and I think that's the negative aspect of the paper. And I fear that it is especially happening with people who are not super statistically educated or just know some basics, but are not really understanding the details of statistics and of the methods used. And they might now get this. So it's not only the press, the people who don't do fMRI. What I just learned, unfortunately, at a conference, that also people who do fMRI start to not trusting what they do anymore, don't trust their thresholds and so on. And I think that's a real damage, because even people in the field start to say things like, we know we cannot trust fMRI. And I think that is, for me, the most alarming outcome of this, because it makes not only outside a bad press, that people look outside, say a physics guy says in astrophysics, I always knew these fMRI do this weak soft data from the brain, and they don't know what they do. A lot of papers are wrong, so I don't trust anything I see in this. So that is the one negative aspect from outside. The other one is from inside, which I found even more alarming, that people now who may not be statistically super inclined start to say, I don't trust my own data. This is significant with a certain threshold, but we know we cannot trust it. The thresholds are no longer trustworthy, and so on. So that damage is going very deep, because people might decide not to do the study, not to go in this field, not to publish, becoming very unsecure. And of course, people should be educated, should know as much as they can, but we have not all the time to become super statisticians. So therefore, it will be that people from cognitive neuroscience, psychology, medicine, they do good fMRI research, and it should be published. They should trust what they do. And the paper has apparently, this I at least recently learned, also the effect within the, parts of the community to make them so unsecure that they react very negative and strange, in my opinion. And that's completely unjustified, as the correction of Tom Nichols and the authors show. They go really retract substantially from their claims but it's too late. I mean, who reads now the correction? I don't know. I think the press for sure not. So they have now their opinion made, and that affects us all. If we publish now in good journals, they might start just to not send it to review, because they think, it's another of these dangerous fMRI papers. I mean, the damage is even for my career and my PhD students. They might not publish as well anymore, because there is, at least in the non-special journals like Neuroimage, that should be fine. But if you go to Nature or some really top journals, they might just have now the editors who are not experts in fMRI might have now the feeling, that's a dubious field, I should not send this out for review. I mean, that's the damage I really see coming.
So is this a concern of you, or did you really experience some trouble regarding journals and publication?
I would say not yet, because since the summer we have now submitted a few journals, so we have to see what the reviewers say. But I cannot say that I have already a first-hand experience. I think in one review which came in, people asked just some looking at the same data with other statistical methods, which is okay. I mean, this is okay, because that's not too negative. But we have to see. I mean, it's still early days after that paper. Publication and stuff takes time, because the review process takes a bit of time, reviews and so on. So I think in a year from now, we know more whether this really has this negative impact on the field. But I fear that this comes to some extent. I cannot predict how much, but I fear that will come.
Okay. You wrote a kind of statement on your personal blog about this topic, and I will surely put a link on my podcast also. At the end of your statement, you put a more general advice, as you call it, for the readers, that they should inspect their time courses. So could you a little bit elaborate on this?
Yes. I think I see, unfortunately, this paper in a series of papers. This is it's not the first paper to set first the context why I wrote this. The first it's not the first paper which criticizes fMRI statistics or analysis. There are several papers which criticized before what some people call double dipping, which is of course bad. I mean, in the sense that you use data, do a statistic, and then you use, so to say, already the active regions from statistic 1 to do another statistic, which is in some sense double dipping, because you basically exploit already a statistical first test, and they're no longer independent, and so on. So there are other papers criticizing some people's practice on analyzing fMRI data. And what I meant at the end is a bit this larger context, namely that critique on fMRI statistic, as long as it's constructive, is good. But if it leads, again, to what I said before, that people in the field become very unsecure what they're allowed to do, then it has maybe a negative effect. So that means that if people who find the cluster significant, say with cluster thresholding, with any method, if you would then click on this cluster and look at the time course, that was what I meant at the end, and you see the time course averaged over subjects, or for each subject of a certain 20 subject study, say 30 subject study, and you see the time course look really not like bold, that don't have a 5-second delay and rise and fall down, but there is some ups and downs which might lead in some statistical tests still to significance, because it might be some effect. Of course, statistics should protect you from this, but who knows? So the point is, it is reassuring if you look at your clusters and look behind how the shape of the response looks like. This is what I did since my first days on fMRI. You get the feeling, oh, I can trust that cluster. It looks bold-like. And that is a feeling we should not forget. And that doesn't mean I do another statistic. Statistic is already done. I just look at the already thresholded clusters, how the time course looks like, without claiming I run another statistic on that. But it's reassuring to do that, because you know then, is this potentially noise, which we have not protected for, like the inflated ones? I would predict that if you look at the clusters, which were weakly significant and via the inflated issues discussed in the Eklund paper, I would guess that some of these clusters would not show a bold-like response. Some strange ups and downs correlated enough across subjects for some reason that it reaches significance. And you could protect yourself by simply inspecting the time course. And if it's so weak that you see nothing, even in the average, okay, then you can still think, okay, I still trust it for some reason, but I would start to get doubts and would reanalyze it, would check it, would not publish maybe completely weakly thresholded data, which doesn't show any sign that's a good fMRI bold response. That's what I meant at the end. And my critique is extending beyond the Eklund paper to the whole series of papers which make our people in the field, not Voyager users, I mean generally users of all software, make them insecure. Oh, I'm not allowed to look at these clusters because then I might do double dipping, and some people might just think they do double dipping by looking at it, but it's not double dipping. But it prevents and fears people to do it, and this I don't like. I think we should know that our data is complex, and to reassure you that the data looks like the assumptions suggest they should look like is something very helpful. And we have so many complex pipelines to reassure that our end results still show bold-like response, and not just look at a map and finish with that, is what I meant at the end of this blog. And yes, I just want to encourage people to do this more, to understand really what double dipping means and what it does not mean, and to try I come from I studied in Germany, did my postdoc in Max Planck Institute, and if I see how people say with monkey data, with electrophysiological data, look carefully at every stage of their data and check and check and check. I took this model over to fMRI data, and I think people should do this more. And Voyager, of course, is also especially, would not say easy, but at least it welcomes that people explore and look at their data. And I think that is also why I did that in that software, because I want that people know what they get at the end. And I think, good scientists have this tendency to do that, and we should also do this in fMRI. I think it would prevent us. I would never publish a paper where I see, in the cluster I discuss the most and say this shows now that we found X, and then I see it doesn't show any good bold response. I mean, I would not publish that, honestly. Even if some software, some cluster threshold tells me it's significant, I would not. I would go back to the drawing board. This is what I mean.
Well, I managed to get Tom Nichols, who is one of the authors of this paper, into this podcast. Tom Nichols is a professor in Coventry at the University of Warwick in the Department of Statistics. He has published numerous papers regarding methods of analyzing neuroimaging data.
Well, so I should say that this publication started as what we call a technical report or a preprint. So we released it to our colleagues, November of 2015. So we have been getting feedback continuously, and some of it critical, but much of it supportive and sort of worrying, like expressing, oh my goodness, what have you found here? So my initial emotion with the publication was happiness that we got this rather methodological, very statistically oriented publication in a sort of a high-profile venue. And oftentimes I think statisticians struggle to get a methodology published in high-profile locations, and so I was very happy that we were able to communicate this with such a forum. And what's more, the publication was made public on the week of the Human Brain Mapping Conference, where I was in Geneva with all my colleagues, and so it was a very positive feeling there. In the next month, however, there was much consternation from some of my colleagues, never about the actual content of the work. No one has disputed, the core findings of our work, but the way in which we interpreted it and the careless use of the estimate of the number of studies impacted by the finding. And of course, this was this notorious 40,000 statement that we basically implied that the entirety of the fMRI literature was affected. Now, and it was careless, but our motivation there and why I don't know how many times I read this draft and this just I just skimmed over this. We found that our findings affected this one type of inference, this one type of finding signals in brain image data known as cluster-wise inference. And this is the more common of the two types of inference. And so we found the problem not with voxel-wise, this other way, but with cluster-wise. And so we thought, wow, we found a problem with the most commonly used inference procedure. This is quite serious. But when we were challenged on this, I went and I did some back-of-the-envelope calculations and found that, of course, it's much smaller. It's something just under a tenth of this literature, perhaps, has results that would be altered by our findings.
Do you think it's only the problem only affects activation mapping studies, or what about functional connectivity and multivoxel pattern analyses?
No, our findings only apply to task-based fMRI. Our purpose was to evaluate the well-established and frankly the three tools that actually do really the same thing fundamentally. They have slightly different assumptions, slightly different methods, but at the end of the day, they're all doing the same thing, looking to localize changes in brain activity induced by a task. I think there are lots of great questions to ask about functional connectivity and MVP-PVA, but there's less of a single tool that people use, and there's more differences in the way people do things. So it's harder for us to do an evaluation that would have as such sort of wide scale applicability or implications as we did, simply because task fMRI is mature, it's 25 years old, and by and large, the methods that are used for task brain mapping are pretty fixed and common across the literature.
Mm-hmm. I read that there's a story behind the correction in the PNAS paper. So many people criticize that your assumptions were too far-fetched with the 40,000. You reduced it somehow, but the journal, there's a story that the journal was not very keen to do this correction right away. Is it correct?
Yes, I wrote a blog post about my experience with that. The response from the journal was that since the core findings of our paper were not perturbed, no one was debating that the exact experiments that we conducted were faulty or the precise conclusions we're drawing from those experiments were faulty. They said, no, this is just interpretation. It's not a correction. Sorry. And I had some understanding, sympathy, maybe, but then almost right away, thanks to Twitter, someone on the internet went and searched all the corrections that appeared at PNAS, and lots of trivial things, author initials, little misstatements were corrected in PNAS. So that was rather odd in retrospect why they would decline to do that. And I suspect it's because it was a very high profile paper and was getting lots of play in the media. They didn't want to entertain that. Anyway, I appealed to the editor And fortunately, they quickly changed their mind and said that they would publish a correction.
Yeah, great. I mean, this is a great experience to have so many people in the community to support you in achieving a specific goal regarding a publication or a correction, right?
Yes, well, I would have rather it not happened at all, but yes.
Yeah, correct. So, what was the reason that you didn't include brain Voyager on the analysis?
Oh, that's a good question, and it's simply a lack of familiarity with it. I mean, also it's not free software, so we would have had to pay for licenses. So I think it's just a coincidence of the union of software packages that myself and Anders Eklund were familiar with was these three. And to be honest, AFNI was already at the sort of the edge of our familiarity, but it was the third most used package, and so we just thought it would be great to extend it to that. But I suppose if I had a license, I would have used it, but we didn't. We're not users.
Okay. I was trying to interview Robert Cox from AFNI also. Didn't manage it yet. It seems that he was willing to do it, but seems to be kind of annoyed, of course, because AFNI was so in the focus because of this bug you found. What was the story behind this? The bug was already changed, so it was corrected when you finally had the paper out, or was the timeline there?
So it's a good question. So I said we put this paper out as a preprint in November 2015. We have been working on this for over a year, and as soon as we identified these problems with AFNI, we contacted Bob Cox, and in fact, we went to all of the creators of the software as we found these problems before we published them even as a preprint. We took our results to them and said, "Hey, what do you think about these?" And we got some useful feedback. And Bob was fantastic, and as soon as he saw the problem, he went and fixed it. And so I think it was in May of 2015 he'd already fixed this problem. But it was simply because we expected the AFNI program to do better than it was doing, and so we actually kind of went and re-implemented what AFNI was doing. And then again, we're perplexed that we're getting different results, and that's how we ultimately found the problem.
Mm-hmm. When I talked to people about this publication, a lot of people said, okay, one point is it's maybe too far-fetched. It's not a problem from fMRI studies, from neuroscience. It's a general statistical problem in biomedicine, in genetics. We have huge data sets. What do you think of this?
Well, I mean, it's simply about the tools you use. Yes, we did focus on small sample sizes because that's where a lot of publications are done. But I think it speaks to the importance of validating whatever tool you use in the size that in the sample sizes that you are using it with. So, for example, there's another publication that I've done that's somewhat similar with a then student, Matt Silver, at Imperial College London, where we did this similar kind of evaluation using structural brain image data, not functional, but structural. And we set out to validate whether this cluster size inference procedure would give the expected false positive rate in a setting where they have hundreds of subjects. And frankly, it was a small master's project. I knew what the answer should be. I thought, these methods, they always work with sufficient data. This is a no-brainer. It's a nice little concise project. Someone else had done this evaluation for voxel-wise inference and it turned out fine. Let's just do this for cluster-wise because that other work should have done that. And in fact, we found that for real data with this structural brain image data, even with 700 subjects, this one variant of the cluster size method using a lower cluster forming threshold was giving inflated false positives. And that really surprised me, and that was giving me a hint like, this is even with tons and tons of data, not everything works. So I think it's a general lesson of the importance of validating, whatever it is the tool that you're using. And I think it varies by disciplines, but I think a lot of disciplines do take this seriously in the validation of their methods. And I think it's maybe a little bit in task fMRI because the discipline is so mature. There's just kind of assumption like, well, somebody validated these sometime, right? Long ago, yes? And the answer was yes, they did validate them using computer simulations. And it's only now with this vast quantity of this empirical data that we're able to do the empirical evaluation.
I mean, you used real resting state data and made a lot of analysis over it, right? So the one concern was also that maybe resting state data are not the same as task fMRI data, so there should be a difference, and this should be somehow smaller your claims.
Yes, this is something that we struggled with in this pre-publication state. We had lots of feedback about, is it really appropriate to use resting state data as a surrogate for task data when there is no effective task? And we carefully took that on in the paper. There's the first piece of information is that if you take a task experiment, data where there actually was a task, and then you subtract out all the signal that you can explain by the task, you get what we call residuals. And then if you take those residuals and you look for the patterns of resting state correlations that are sort of well known and why we collect all this resting state data, and if you look for it, you will find those same patterns. So that's saying that the structure, the spatial structure of this data, of resting state data, can be found in task data after you take off the effect of the task. So that right there is telling you that there is some important similarities between task and resting data that supports the use of the resting data as a surrogate for null task data. The other thing that people were worried about was, are there transient effects? So in the first, say, 2 minutes of a resting state experiment, is there something special that's going on that's common across individuals? I mean, no, there's no task, but is there something consistent across all the experiences that people have? And that is basically mistaking something, basically is inducing some common variation that we would mistake as a false positive when we're really actually detecting something, right? And the way we refuted that was that we looked at 4 different experimental paradigms. So some were a fast on-off paradigm, some was a slow on-off paradigm, and we also looked at something called event-related paradigms, which are comprised of sort of discrete events, and we looked at 2 different arrangements of them. And across all of these experimental paradigms, we still found this problem. So if there was something consistent, across subjects in this resting state data that was inducing, signal that was actually something interesting, it's not really clear how that would be the same across all these different designs. And yet we found that these inflated false positive rates across all the different designs. So that's the other key piece of evidence of saying why these results, I think, are important, even though we're using, a different type of data than task data.
Before, I would like to talk to you about your publication, and as it reflected in the mass media. What about the new kind of sequences like multiband or grapper sequences? Do you think there are more problems with that regarding your false discovery study?
This is a current area of interest of Anders Eklund in particular, to look at the false positive rates that you get with the multiband data. I would say that if anything, the multiband data is going to have more complex spatial structure than we have in the traditional acquisitions. And so if anything, there's going to be yet more challenges for the traditional random field theory results that give us the standard inferences that we're examining. So I think it's important to look at it, but I think there's no reason to think that it's going to be better for that kind of data. To be honest, there's so much variation in there that I think that has to do from the biology, the long scale correlation in space. I think that's mainly coming from the biology, not so much the acquisition. So I frankly don't think it's going to be that different, but it'd be great to do that evaluation as well, and that's something that Anders is looking at.
Mm-hmm. Okay. I think many people think that your publication did the research community a favor to spread this information and to start this this debate about this. There were also critical voices that say brain research is now in kind of defense position. Most people, common people, think all we have done in the last 15 to 20 years is completely erroneous. Do you think it's not your responsibility to how the mass media put on the headlines or the titles, or do you think it's somehow in your paper that you haven't been clear enough, and it's that you change it a little bit in your correction?
So I'm certainly surprised by the way the result was taken up by the mass media. We have some responsibility to bear on that with the kind of the statement about the 40,000 implying it's the entirety of the literature. But I was really surprised by the number of voices that were poised to criticize fMRI as a discipline as a whole. I was really, it is not the case that this one single paper, created all this antipathy. There was a lot of people who have a lot of critical opinions of the methodology, of the method of fMRI, and I was unaware of that. I honestly was. So if I were to do anything different, certainly, obviously, we would have had that we would not have had the statements that implied that this affected the whole of the literature. However, it still was not a trivial portion of the literature that was affected, and it pointed out practices that I think needed to be addressed. That is, a continuous and consistent look at validation of the methods that we use using empirical data. So yeah, I was, what can I say? I was disappointed by the way it was reported in the media. In fact, just today I was forwarded a link and someone said, hey, look, they quote your paper and say 70% of the literature is wrong, which of course is a complete misunderstanding of our paper.
Yes.
Which is just to be clear, we found that in some settings, that is the worst, least favorable setting, we found up to a 70% false positive rate. That is, when the software is working, only 1 out of 20 experiments should show any false positives. And we were saying that under these settings with purely noise data, you could get up to 70%. So up to 70% of the experiments would produce a false result. But this is under the case where there's nothing going on. And that, of course, is not, that may be some portion of the experiments, but by and large, we expect that most experiments are successfully inducing experimental variation, and hence there is an inflation of effects that are present. That's the one possibility of inflation of the significance of the effects that are there, or there is actually sort of false positives that are mistaken for effects that then later are replicated, or the third case is simply they are false positive. They correspond to effects that are not real. So, but unfortunately, and the problem is we don't know what that breakdown is in the real literature. So even among those 3,500, this roughly one tenth of the literature that is affected by our findings, you basically would have to go through each and every one of them and find out. So for example, if a paper has results that have very strong significance, well, those results are not going to be changed by a slight change in the strength of the significance. In contrast, if the results are just barely significant, well then, if they've been revised with methods that corrected this, maybe those results wouldn't be significant. So it just takes, you'd have to look at each and every result. And that's one of the big take-home messages that we had, is that because of the poor state of data sharing, none of these results can be revisited in practice. And which is really, really a shame. And if you look at other disciplines like genetics, it is just a requisite. When you publish a whole genome analysis, you must report the significance for each and every genetic marker you examined. Now, does it go in the body of the paper? No, you can't include all that, but there's a table or some other file that's shared, and we do not do that in brain imaging, and it really boggles the mind that we don't do that.
Are you able to make a kind of 5-point or whatever bullet list what everyone should check before publication or before analyzing their fMRI data? So what kind of take-home messages, additional messages for everyone, what to check, what to look at, what surely not to do with your data?
So if I were to identify practices that really need to be followed by practitioners, I think the simplest thing is this issue of multiple comparisons correction, or multiple testing correction, as it's also known as. The issue is that we search over the brain for activations, and there are many opportunities for false positives. And when I was looking into the issue of exactly how many studies did our results affect, I was shocked to see that a large portion of the literature was not affected by our results simply because the literature had not used a correction for multiple testing. And it's really unexcusable at this day and age that you would have results that don't do this very fundamental correction, that every best practice document, book, textbook says you must do this. So that's the first sort of practice I think that people need to do. The other thing is to have incredible criticism of results that are just near the borderline of significance. So as I was mentioning before, if you have a result that is really strongly significant, that's good. I mean, you still want to turn it upside down and look at it, but you need extra strong criticism of a result that's hanging at the borderline, because whenever you are really depending on the exact p-value you have, that's the measure of significance, you are making assumptions about the data. And the more precisely you need to rely on that exact value of the p-value, the more strongly you're relying on those assumptions to be exactly satisfied. So that's the next thing. So if you have something that's very marginally significant, well then for goodness sake, look at the data at that location. Is there heterogeneity? Is there outliers? Are there things that could be an artifactual source of the significance that you're seeing? Because you really want to know, I hope the data are well behaved there, because I'm really depending on all these statistical assumptions to be working and satisfied. The other thing I would say is, and this was one of the main takeaways of the work, was the use of these non-parametric procedures. So these are procedures that do not make assumptions about the data. They're really not controversial if you look into genetics, and especially microarrays and other analyses in genomics. Permutation tests are not uncommon. They're a tool that are used. They're not controversial. And in brain imaging, we are very lucky that we have a very challenging type of data with the spatial data with spatial correlation, and we have some really, really exciting, cool mathematical results that gave us ways to make inference with this spatial data. But they're grounded on all these assumptions, which our work has helped show that are not always satisfied. And hence, if you do not want to be dependent on these assumptions, you should turn to some of these non-parametric methods. And the other final thing I would say, I don't know if I got up to 5, the final thing I would say is that the importance of being transparent in the methodology that you've used, completely describing what you've done and sharing both the statistical results and, if possible, the data that underlies those results. And I don't mean just the data that goes into a plot, I mean the image data. As I was saying, there is no excuse for not sharing the full 3-dimensional image of test statistics. It is basically analogous to what every other discipline in science does when they report in a paper, either through a table or through a supplementary data file. And providing the data that goes behind it, the images for each individual, further gives the opportunity for other scientists to reuse that data, check their conclusions, and basically try to make new science and try to draw new conclusions that weren't necessarily the interests of the original investigators.
Yes. Yes, thanks. Very helpful. What is your look into the future? What are your plans for the next years, and what do you think the neuroimaging community is heading to?
Well, you've already touched on some of these, the importance of the analysis of resting state data to study functional connectivity, and also the use of multivoxel pattern analysis. So using techniques that are more focused on analyzing multiple voxels at the same time, and also using those to make predictions about behavior or making predictions about the status of individuals, sort of comparing, predicting whether an individual has a disease or not, or the severity of their disease, or making predictions about, for example, if you're at a pain experiment, what level of pain are you experiencing? These techniques, I think, are are the way that the discipline is going. And so in some ways, our findings are kind of looking backwards in a way, because task fMRI will remain a core tool of neuroscience, but it's really the foundation which now lots of other things are going to be built upon. And I look forward to developing methods for all these prediction and resting state methods. I look forward to building methods for resting state data and predictive analyses. It's sort of where we're going.
So finally, I discussed again with my wife Dina the topic: what kind of consequences should be drawn from this paper?
The good news of these interviews taken together is that all is not as bad as it seems. Of course, there was a lot of hustle going on about this paper, and it ruffled a lot of feathers, and I think many people were really shocked by these results, and there was a lot of insecurity amongst neuroimagers as well, because they started distrusting their own work. But it's really reassuring to hear these statistic experts say that really there is no reason to be overly concerned, because as Hina Google pointed out, we're not all super statisticians, and we can't all be super statisticians. So we should educate ourselves best we can, but at some point we really have to trust the experts and trust that the software we use does what it's supposed to be doing. What I also find reassuring is that all three of them pretty much agree on what the implications of these results are for the whole field of neuroimaging. And that is that we should all avoid very liberal thresholds. We should correct for multiple comparisons. There's really no excuse for not doing it. And we should make more use of non-parametric procedures. Also, we should all check the quality of our data at each step, and use standard pipelines and standard settings to avoid p-hacking and self-fulfilling prophecies. We should inspect our time courses to get a feeling for whether what's in the data is really bold signal. And there are tools out there that help us do this. And also that we should be transparent in everything we do and how we report what we did and our results. And that we should share our data, not just to give others the opportunity to revisit what we did in our work, but also to provide them with the chance of doing new research on data that already exists, and especially methodologists to help them improve their methods and their models for data analyses, because now they can work with real, actual data and not just simulated data. In contrast to Hina Google, I'm not overly pessimistic, because I think it might have been the wake-up call that neuroimagers needed to get the debate going within the field and not just outside of the field. And as Tom Nichols said, he was surprised at how much criticism was readily thrown at neuroimaging from outsiders. And I think it's not a wise idea to leave the criticism to outsiders, and we should rather try to proactively find solutions to the problems in our field. So, in my opinion, mistakes happen, and it's not important to try and avoid mistakes at all costs, but rather it's important how we deal with the mistakes that have already happened and what and how we learn from them. And I think the way this manuscript was received also, or mainly outside of the field, was a symptom or an indication of the need to stop and evaluate what we've got in neuroimaging and where we should be heading. So one thing that hopefully comes from this is that neuroscientists or neuroimagers will be more conscious of how they put their findings out there, although this is only partly our responsibility, because if the media picks something up and they make a mountain out of a molehill, then you can't really do that much about it, but you can try to phrase your findings in a way that not lend themselves to being blown up by the media. What is our responsibility, I think, is to mind our own business, so to speak. And one important aspect of the solution, in my view, is that how we educate young scientists. So they should be trained to start off best they can, and be educated about statistics best they can, so they can come up with new and better questions, and as a consequence also with new and better answers to these questions. And one thing I hope that does not happen is that it fosters an overwhelming amount of pessimism. I mean, right now people are kind of course they're influenced by this, and of course you start questioning your own work, which to some degree is good. But on the other hand, we need neuroimagers and scientists to be enthusiastic and to be passionate about their work, and distrusting your own results to a great degree, I think, could definitely be harmful to the field. So I think now we should, as a community, try to follow these suggestions that were put forth based on these results by Eklund and colleagues, and seize the opportunity to push for solutions, because there really is no reason to fall into despair. It just points to the importance of pausing and re-evaluating and finding solutions and then moving ahead. I think what each of us can do, aside from being transparent and to do our best to be statistically correct in our work, is that we should instill enthusiasm in the upcoming generations of academics or scientists, and to make them even better scientists than we are. For example, I teach SPM to beginners, even though I'm not a statistician, yet I always really enjoyed statistics and programming. And I can say that from my experience, for one thing, basically any subject can be made interesting and fun, even statistics. If you as a teacher are enthusiastic about it, then there's a good chance that you will get a lot of your students excited and enthusiastic about your topic. And the other thing is that if you teach a topic to others, then you also learn a lot about it that you wouldn't have learned if you hadn't been a teacher. So I think teaching young scientists what you are passionate about is good for both ends, because it gives the students the chance to be enthusiastic about your topic, and gives you the chance to learn more about it.